And thanks everyone for tuning in this afternoon. So we are going to be talking about drivers of exceptional coastal warming in the Northeastern US. And this work was recently published. And so what we're going to do is I'm going to talk for the next half hour or so, 35 minutes, and I'll describe all the results from our study. And then I'll hand it over to Radley, who will talk about the implications of our work for climate assessments in the region and climate impacts. So motivation for this work, if you look at the observed pattern of warming over the last 120 years, you clearly see that the Northeastern US, especially the coastal part of the Northeast US, has experienced substantial warming. When you compare it with other parts of the continental US, it's quite clear that these coastal regions in the Northeast have experienced about over 2 degrees Celsius warming so far. One thing we find is that you'll find this map in National Climate Assessment Report or other assessments, but we don't really know, or none of the literature really talks about why there is this enhanced warming along the coast in the region. The other piece is that there is ocean warming adjacent to the Northeast as well. And this particular result is from Pershing et al. 2015, showing trends in sea surface temperatures in the global oceans. And you can clearly see that the Northwest Shelf region of the North Atlantic, which is adjacent to the Northeastern US, has experienced substantial warming over the last few decades. I'm not showing you projections here, but if you look at previous work looking at projections over land, we've done some work showing that if you focus on the rate of warming in the future based on climate models, you find that the Northeastern US is one of the fastest warming regions in the lower 48 states. Similar results exist for ocean warming as well, showing that sea surface temperatures in the Northwest Atlantic are also projected to warm at a faster rate. And there's a fair bit of work showing the impacts of that ocean warming on fisheries in the Gulf of Maine. And Michelle Stodinger's review article in Fisheries Oceanography is a really good article summarizing all the impacts that we find on fisheries in the region. So the question here is that why is there this enhanced warming along the coast? And is it in any way related to substantial warming that we see in the adjacent ocean? What we do in this work essentially is there are two parts to this work. One is just characterizing the spatial pattern of warming, and then the other piece is understanding what the drivers of that warming are. So I'm going to be focusing on the first part first, of course. And what I'm showing you here are this is a comparison between seasonal temperature trends for the coastal NEUS shown in red and for the entire North American land areas shown in gray. And if you focus on warming in the annual mean, you clearly see that the coastal NEUS shown in red has experienced substantial warming, and it's relatively high, compared to much of the North American land areas. This is mainly because the region has experienced significant warming in summer and fall seasons. And you can see that when you compare warming in the North American land areas, the coastal NEUS shows highest warming in the region in both the summer as well as in the fall season. Overall, the warming is higher in winter in this region. And you might think that there are other regions showing higher warming in DJF and MAM, which is winter and spring. What I want to point out here is that this higher warming is because there is typically higher warming at high latitudes in winter, and much of the highest warming totals we see here is because of the northern parts of Canada and Canadian Arctic. If you look at all the latitudes, at the latitudes similar to the coastal NEUS, you would find that this pattern of higher warming along the coast in this region is present in winter and spring seasons as well. Since we have higher warming in summer months, that's what I'm going to focus on for the next analysis. Now, this previous analysis that I showed you was based on one observational data set. What we wanted to see is whether this pattern of higher warming along the coast is present in other data sets as well. So here you have 4 different data sets that we've looked at. These are all observational data sets. The top 2 data sets have relatively high resolution, and the Berkeley Earth and 20th century reanalysis data sets have relatively low resolution. And then these dots show you comparison between warming trends along the coast in red and in the interior NEUS in blue. And what you see here is that even though the magnitude of warming is different in different observational data sets, all of these data sets indicate that there is higher warming along the coast and relatively lower warming in the interior NEUS. So that warming contrast between coast and the interior regions is quite obvious in all 4 data sets. Another thing to notice here is that the warming that we see along the coast is not just exceptional when you look at northern hemisphere, North American land areas. It's quite exceptional on an hemispheric scale as well. So the black histogram is showing you warming trends across all northern hemisphere land areas, and you can see that the coastal NEUS warming in high resolution data sets is the highest, or some of the highest warming trends that we see over the entire hemisphere. And just to highlight that point further, this is showing you the spatial pattern of warming in summer of the whole northern hemisphere. And the color scale is such that all the bright yellow regions are showing you regions that have experienced warming over 2 degrees Celsius over the last 120 years in summer. And if I were to zoom in on the northeastern US, you see that this coastal part of the NEUS has experienced over 2 degrees Celsius warming. This turns out to be, we say it's exceptional warming because if you were to calculate how much land, the fraction of land area that has experienced over 2 degrees Celsius warming, it's only 4% of land areas in summer in the entire northern hemisphere that has experienced over 2 degrees Celsius warming, and the northeastern US is a part of that. And so that's why we show in this work that this coastal region of the northeastern US has truly experienced exceptional warming. So what is driving this change? And I'm giving away the answer here, but there are 2 factors that are essentially responsible for this exceptional warming. One is the SST increase in the Northwest Shelf region, and the other one is the atmospheric circulation changes in the North Atlantic. And I'm going to spend 5 minutes, talking about why these 2 factors are important. So the SST increase in the Northwest Shelf region is connected to the slowdown in Atlantic meridional overturning circulation, the AMOC. And the AMOC is a large system of ocean currents. It's like conveyor belt circulation that carries warm water from the equator towards the pole. It gets colder, it sinks, and then it travels at depth towards the equator. And this circulation essentially is responsible for carrying heat and salt throughout the ocean. The previous work has shown that this current is actually, the AMOC is slowing down. And one consequence of that slowdown is higher warming, stronger warming in the Northwest Shelf region, and cooling in the south of Greenland in the subpolar gyre region. And this warming in the Northwest Shelf region and cooling in the subpolar gyre region is, it's called the surface fingerprint of a gradual weakening of AMOC. Now, this is important because what's being shown is that this weakening of AMOC is associated with the northward shift of the Gulf Stream. And as that as that warmer water current moves northward towards, closer to the coast of the northeastern US, it dumps more heat in this region. And as we know that this northwest shelf region is relatively shallow, and as a result, it's warming faster. It's typically affected by colder Labrador currents, but because the Gulf Stream is moving north due to weakening AMOC, that is dumping more heat and heating up this part of the ocean. What's been shown in climate model simulations is that if you were to use high resolution ocean model and try to understand what happens when you increase greenhouse gas concentrations, what you essentially find is that when you quadruple the level of CO2 in the atmosphere, it leads to much higher warming in the Northwest Shelf region. So one consequence of this result is that higher warming or increase in CO2 concentrations, greenhouse gas concentrations in the future will likely lead to a weakening AMOC circulation, and that would lead to higher SSTs in the Northwest Shelf region, which is quite important for our study. The other piece in the puzzle is the atmospheric circulation changes in the North Atlantic. And I'm specifically focusing on the North Atlantic Oscillation here. North Atlantic Oscillation is a mode of atmospheric variability in the North Atlantic. Sea level pressures oscillate in the North Atlantic, and that affects the entire atmospheric circulation. One consequence of that circulation, or rather that sea level pressure variability in the North Atlantic, is that it changes the strength and the position of the jet stream. When the jet stream, or when this North Atlantic oscillation is in the negative mode, jet stream is a lot wavier. We have this trough over the eastern United States, and that brings in cold air from higher latitudes. When the NAO is in the positive phase, the jet stream is more zonal in nature. It's located slightly to the north of the eastern US, and we experience slightly warmer conditions, relatively warmer conditions. So what I'm going to show you next is that the reason why we have enhanced warming along the coast here is because there is SST increase in the Northwest Shelf region that is linked to a weakening AMOC, and it combines with the atmospheric circulation changes due to more persistent positive NAO conditions. So the first step is to understand the mode of variability that describes this change that we've seen in AMOC over the last few decades. And to be able to do that, what we do is we take the global SST field and we do the EOF analysis on that field. And one of the modes of variability we find is this pattern of correlated, but changes that are correlated but of opposite sign south of Greenland and in the Northwest Shelf region. And as I described earlier, this is what we call the spatial fingerprint of AMOC weakening. I'm just showing you this analysis was done for the entire global SST field, but I'm just showing you result that's focused on the North Atlantic because that's what we are interested in. If you look at the temporal evolution of this pattern that is shown by black line here. So essentially this black line time series, which has a long-term trend, is describing how this AMOC has varied over time. And the long-term trend indicates that the AMOC circulation has weakened over time. The other two curves shown in blue and red are AMOC indices that were derived in other studies. And we show in this work is that the AMOC index that we calculate correlates fairly strongly at multi-year variations with other indices. And so we're confident that what we've identified here is describing the AMOC index. If you were to take that AMOC index and calculate correlations with regional surface air temperatures, you get this pattern right here. It shows strong correlations. So there are strong correlations between this AMOC index shown in black and surface air temperatures over the Northwest Shelf region, and that's expected because, as I described earlier, sea surface temperatures are going up. But there are also relatively stronger correlations along the coast over land in this figure. And so essentially, what this figure is telling you that there are strong correlations between what's happening with temperature over land and this SST variation that comes about because of the weakening AMOC. But of course, this correlation map that I'm showing you is just telling you that there are stronger correlations. It doesn't tell you anything about what is causing those correlations. So to be able to do that, we need to find atmospheric changes that correlate or rather covary with this SST pattern. And so to do that, what we do is we look at geopotential heights at 500 hectopascals. And we do that because in this region, this mid-tropospheric atmospheric circulation at 500 hectopascals is strongly correlated with the surface climate. If you look at temperature variations at seasonal and interannual scales, you would find that they are strongly correlated with variations in geopotential heights at 500 hectopascals. So we do the maximum covariance analysis to find that mode of covariability between the SSTs and the geopotential heights. And essentially what we find is that the mode of geopotential height that covaries with this SST pattern looks like this. And those of you who are used to looking at NAO would quickly realize that this pattern of positive anomalies in the subtropical North Atlantic and negative anomalies at higher latitudes is representative of NAO variations. Now, if you figure out how this pattern varies over time, then that's described here by these blue curves. One is for SST and one is for geopotential height, but they co-vary together because that's essentially what the covariance, or rather the maximum covariance analysis gives you. When you look at the variations in these blue curves, which is describing how this pattern, the Z500 pattern, varies over time, naturally it correlates strongly with the NAO index, which is shown here by red and blue bars. And another thing you would notice is that the correlation between the NAO index and the blue time series is not very strong at interannual scale on year-to-year time scales. It's much stronger at multi-year time scale. So what we are interested in is this low frequency variability in these patterns. So we have found out how these two patterns co-vary together, and that's described by NAO variations by this blue field. How is this related to the surface climate and surface temperature in the Northeastern US? So to be able to do that, what we do is we take this time series shown in blue and we calculate regressions with different atmospheric fields. And so that's what I'm going to show you next. So if I were to take that mode of covariability between SST and Z500, which is describing changes in AMOC and NAO, and calculate regressions with different atmospheric fields, the first result is right here. It's associated with an increase in ocean to atmosphere heat flux in the Northwest Shelf region. So what's happening here is that because the AMOC is slowing down, the SSTs are going up in this region. And as a result, what we find is that the heat flux from the ocean surface to the atmosphere has gone up right along the coast of the Northeastern US. This makes sense. This makes sense when we look at tropospheric temperature trends in the region. What I'm showing you on the top here is I'm focusing on a cross section that goes from the Northeastern US all the way to the mid-Atlantic. And then I calculate temperature trends throughout the troposphere for that cross section. So the inverted triangles here indicate the locations of New York City and Boston. And so you know where the coast is. And then to the left of it is where the northeastern land areas are, to the right of it is the North Atlantic Ocean. And you can clearly see in this figure is that the lower troposphere has experienced substantial warming here. And so that makes sense. If you're increasing SSTs and that is leading to higher heat flux from the ocean to the surface, you would expect that lower troposphere to get warmer. If I go a step further and calculate how that mode of covariability between SSTs and Z500 affects low-level winds, what you find is that it's associated with anomalous winds from the ocean towards the northeast coast. And so when you put this together, essentially, what you find is this idea that the slowing down of AMOC circulation is increasing SSTs in the region, that is warming the lower troposphere, and this anomalous southeasterly winds bring that extra heat towards the coastal NEUS, and it's nudging those temperature trends upwards. And that's what you see in this regression. You have relatively higher temperature anomalies along the coast compared to the remaining region of the northeastern US. So that's really the idea. Those are the drivers that we are talking about. The SST increase associated with AMOC weakening and persistent positive NAO conditions that are bringing in that heat towards the coast. Now, the natural question here is this trend going to continue in the future? Will we experience enhanced warming in future as well? I don't really have answer to that question. We didn't really answer that question in the study, but what we did was to look at climate models to see how well they capture these observed trends. And we looked at 3 different climate model simulations. On the left-hand side is these historical simulations. These are coupled model experiments that we use in understanding how the models are performing, as well as we use a similar setup for future projections. And what you find is this is the common response that you see in most of these models, is that you don't really capture that observed pattern of warming. In fact, what you see in models is the opposite of what you see in observations. There's higher warming in the interior parts of North America, and relatively low warming along the coast, and even low warming over the Northwest Shelf region. The CSM large ensemble is based on one model, but it's trying to capture different flavors of internal variability. And the result is very similar. You don't really see the model capturing the observed pattern of warming. What's in the middle is quite interesting. These are atmosphere-only model simulation that use observed SSTs at the surface. So they are forced by a realistic SST pattern at the surface. And there are also simulations that are done at much higher horizontal resolution. And as a result, what you see is that clearly the air temperature is now showing substantial warming compared to these other experiments, because the model knows what the sea surface temperature trend is in this case. But again, you don't really see the coastal warming, enhanced warming along the coast in this case, and that might have to do with model not capturing that low frequency NAO-like circulation very well. So that's a problem in these models. But all is not lost. What I was showing you was the common response across models, but there are individual models that might be capturing some of these patterns well. And I'm just showing you one example here. This is a particular model run at very high resolution. And of course, this is, again, atmosphere-only model simulation. So the SST pattern is quite realistic, but the model is able to simulate the NAO-like circulation, and that results in slightly higher warming along the coast. In this case, in observations, what we find is that the low-level wind circulation is more southeasterly, whereas here in this case, it's more southerly in this model. And as a result, the relatively high warming is, limited to these coastal regions of the northeastern US. But in general, what I'm trying to say here is that there are certain models that are able to capture all of these different drivers and show patterns that are closer to observations than most models. So that's really the ongoing and future work, is to understand, will the coastal NEUS continue to experience enhanced warming? And that really depends on the future evolution of AMOC and NAO behavior. There's a lot of recent work that indicates that models are saying that the AMOC will continue to weaken in the future. And as a result, the SSTs in our adjacent shelf region would increase. But then we don't really know much about the NAO behavior. What we are interested in this case is NAO behavior at multiple time scales, the low frequency NAO behavior, and that's not really captured very well in these models. And so the next question is, why do climate models struggle to capture these spatial patterns of warming? And that's what we are trying to understand. It might be related to model resolution. It might be related to missing processes in the models, or it's highly likely that it's going to be a combination of many different factors. And that's what we're looking at by looking at different climate model ensembles and experiments. And then the other question, which is quite important, is the analysis of seasonal trends. Most of the focus of my presentation was on annual mean trends, but we've shown in this work that stronger warming is experienced mostly in summer and fall seasons. And that is the case over land as well as in the ocean when you look at ocean temperatures. So the drivers, the mechanisms that we are putting forward, how do those mechanisms work in different seasons? And that will be an interesting thing to look at. So I'm going to stop there, and I'm going to hand it over to Radley, who's going to discuss the implications of this work for climate assessments in these regions and climate impacts. So I'll take questions after Radley's talk. Thank you.
Thank you, Ambarish. I'm just going to show one slide, so hopefully we can be done with this within 7 minutes or so, and turn to those points. So hopefully everybody can see the slide now. Yeah, I just wanted to, and let me try to clear some of these other things that you may see on the screen. Do people see more than just my slide, or are you seeing the slide?
I think you're good, Radley.
Fantastic. Okay, great. So yeah, as Ambarish was saying, let's dive a little deeper into some of the implications, including opportunities for future research, especially in the more sort of applied domain, as we think about the Northeast Climate Adaptation Science Center and some of the ecological dimensions, especially. So I think to me, the really kind of central takeaway is that I think the study does really force us to ask this question about whether the types of assessments, whether national climate assessment, even IPCC type assessments, state-based assessments, have been a little too sort of narrow in their heavy reliance on GCM outputs, because as Ambarish showed, this study is indicative, hints at the idea that the models may be failing to simulate some key processes that could be important for generating future outcomes. So while GCMs, I think, are our most reliable tool for projecting the future, while there are benefits to the kind of downscaling based on those global climate models that a lot of people understandably have really flocked to, this study does open up the idea that there may be tail risks if you're looking at the range of possible temperature outcomes that are well outside of what you might get, even if you tried to use a lot of global climate models and RCP scenarios. So what are the implications for that is something to think about. Not saying it's probable, but saying it's possible and maybe worth considering from a risk-based perspective. I think the other real takeaway to me is it's great to see these annually averaged and seasonally averaged results, But what does this imply for individual days, individual nights along the coast? Is this part of the story for why we're seeing so much evening warming, especially in summer in a lot of parts of the coastal Northeast? And humidity, of course, often part of that story when nighttime temperatures are high. But to the extent that those temperatures are high and the humidity is high as well, that's an interaction that should be explored, more deeply because of its implications for human health and for various other large mammals as well. And then we didn't go into the microclimatic dimensions very much. But as we're focusing more and more in the Northeast in the CASC and in other projects on urban communities, vulnerable communities facing urban heat islands, I think an open question and one worthy of more research. How different does this story look in various microclimates? And a related issue, even outside of cities, this coastal breeze that we're all sort of used to relying on across the Northeast, and that has huge historical socioeconomic dimensions to who's in places that have access to that sea breeze and the cooling it provides. How might that change? How has that changed, and how might it continue to change in the future? Is a really important microclimate dimension. So, and of course, a lot of impact models of various types, whether it's ag, forest models, individual species models that folks are working with. A lot of them, of course, do already work at fine temporal and spatial scales. But certainly, to the extent that some models don't and are relying on the seasonal averages or the averaging across a larger domain that might extend inland from the coast, we need to really be open to the idea that the actual impacts can be very nonlinear as temperatures, for example, rise just a little bit. So there's real potential for nonlinearity in the impacts that I think the study points to as well. And also, I guess, sort of consistent with that theme of nonlinearities and surprises, thinking about the implications that go beyond temperature and atmospheric humidity. What does this study imply for how much precipitation could change across the coastal Northeast? Even potentially simultaneous coastal flooding impacts with rainfall and temperature. When we think about the fact that the NAO, for example, is related to variations in sea level height across the Northeast. And perhaps more importantly, as we think about really extreme individual events associated with extremely high precipitation and actual storms, how might this warming pattern in the ocean, coupled to any atmospheric changes, shift the potential for, say, large snowfall events, large rainfall events? These are things we don't really know yet, but want to highlight that when there are sort of emerging correlations between individual variables, the effects can be extremely nonlinear, even if the individual variables, change only, say, 5% or whatever. So that's that kind of correlation across variables, something that we need to spend more time on as well. Ambarish really made this point already about trying to unpack this phenomenon by season. The one thing I'll highlight is when we talked about the summer results, understandably we talked about that warming right along the coast. But of course, there's a lot of emerging research talking about why the suppressed warming in summer might exist in terms of Ohio Valley and some points south. Is that totally distinct, or is there some sort of interaction between other phenomena, such as changes in agricultural productivity that could potentially be leading to more evapotranspiration in summer and helping suppress temperatures a little bit further inland? That's another one of these areas really I'm just bringing up just to highlight that so much more work remains. But the other side of this coin, when we talk about the summer warming along the coast, is the high summer warming along the coast is the suppressed warming in areas further inland, which might partially, not fully, be explainable by some of those increases in evapotranspiration, which can hold down summer temperatures, especially daytime temperatures. And then Ambarish, alluded to the importance of specialized modeling experiments, where we force these interactions more between the ocean and atmosphere. What happens if you actually run some experiments at very high resolution, driven by a forced ocean signature, for example, could help us learn more about these interactions. As Ambarish mentioned, it's extremely complicated given the long periodicity of AMOC and even NAO to some extent, having a multi-decadal signature that's not fully understood. It's really challenging to say what the natural variability parameters are, and that's obviously, critical to trying to say how it might be changing with climate change, and where things might move in the future. And similarly, it suggests that this historical record of whatever it is, 100 years or so, not only isn't enough to fully let us understand the natural variability of, say, AMOC or the NAO, but also makes it extremely, difficult based on observations to fully explore the interactions between those two, how they're affecting each other. So specialized, modeling experiments can help with that. And I guess that last point is related. I think it's inevitable when we get an extreme winter snowstorm, devastating, heavy rain event like hurricane like Ida back in September. People want to know how some of these emergent phenomena might or might not be involved. And there's a lot of speculation here, but if you're a planner trying to consider low probability, high consequence events, certainly you want to be thinking about, open to this notion that interactions between warming along the coast that's maybe faster than climate models thought, possibly coupled to large scale phenomena, even larger scale than what Ambarish described here, changes in Arctic sea ice and northern hemisphere circulation more generally, could in theory interact in complex ways and in ways that our models sort of lack the vision to capture. So it's another one of these sort of low probability, high consequence events that's, I think hard to say anything very definitive about. But if we don't acknowledge that there may be some of these blind spots in our systems, I personally think we're kind of doing a disservice and maybe run the risk of sort of focusing on false precision, for example, by just downscaling based on global climate models if we convince ourselves that that's the full range of possible outcomes. So I think those, in my opinion, that Ambarish's study just raises a whole series of really thought-provoking questions in the science domain, but also in the impacts management policy domain. And like all really impactful studies, I think it raises as many questions as it answers. But I think it's really important that we think about this. And of course, I've just been talking about the climate dimensions, right? All of you with your expertise in ecological systems, species, could point to all sorts of other interconnections and feedbacks. I'm sure your minds are thinking of some of those things, but just the climate dimensions alone, I think the study points to a lot of really, really thought-provoking things that Ambarish unpacked. So I'll leave it there.